All right, so just a short video to introduce our last chapter, which is finite difference methods for initial value problems. So in chapter 8, we looked at boundary value problems. Now we'll look at initial value problems. As you'll see, there's some additional considerations that we need to be concerned with, and it builds on the same finite difference Taylor series expansion basis that we had, but there will be some additional issues that we need to address, and there's a longer list you can see here of methods, but they're all fairly tightly related, so it's not too complicated. So let's just introduce. If you remember back in section 7.2.1, we had the forced spring mass system with drag. We derived the equation. This was the one that we used to illustrate the numerical solution procedure. So we derived this equation from F equals ma, and we had a second order. So here's a second order derivative, first order derivative, second order ODE for the time evolution, basically the position of the mass as it went up and down. So as usual, when we write down differential equations, all the stuff with u's, which is the dependent variable, goes on the left. Everything else goes on the right. We usually refer to that as a forcing term, which makes it non-homogeneous. The main difference now is for initial value problems is you'll notice that the independent variable is time rather than x. So it's a time evolving problem rather than a spatially changing problem. And now we have initial conditions rather than boundary conditions. So the boundary conditions were on either end of the domain, and now we have initial conditions that apply at t is equal to 0. So typically we'll have a position and a velocity. Of course, velocity being the time derivative of the position. So the way the methods will work is we're going to have a time domain which starts at 0. Let me put that up here. So time domain starts at 0, and we'll index that using n. So n instead of I, n is equal to 0, corresponds to the initial condition t is equal to 0, then 1, then 2, and then 3, and then so forth. And so we talk about the methods marching forward in time. We're going to start with the initial condition, which we have here. Start with the initial condition at t is equal to 0, and then march forward in time. So what you'll see is a generic n time step and an n plus first time step separated by a delta t. So instead of delta x, I plus 1, I minus 1, it's now delta t and n plus 1. So we'll talk about the previous time step, which is the nth time step, and the next time step, which is the n plus first time step. And then this just slides through the time domain as we march forward in time. The classification of methods is based on really two main issues, and then there's a whole bunch of variations underneath them. But we either have single-step or multi-step methods, and then explicit or implicit. And these are mutually exclusive, so you could have a single-step explicit method, a single-step implicit method, and so on, as you'll see. And this is why we end up with more methods for initial value problems. But let's talk about the single versus multi-step first. So this is exactly what it sounds like. We talked about the marching in time, so a single-step method takes the solution at the previous time step and gives us an equation to update the solution at the current time step, at the n plus first time step. So we just progress one time step at a time. A multi-step method still progresses one time step at a time, but it uses the information, the solution that we've obtained at more than one previous time step. So you see here it's step singular, here it's steps plural. So we're still computing the current time step, the solution of the current time step, but using multiple previous time steps. So that's single versus multi-step. That's easy to remember. The other distinction is whether we have an explicit or an implicit method. So this is similar to the idea of Gauss-Seidel, SOR, versus some of the other methods where we have an explicit expression for the solution at the current time step. So an explicit expression means that you can solve for one unknown, only one unknown, and that's the solution at the current time step in terms of other things that you know, such as solutions at previous time steps. So those are explicit. So you have one unknown equal to a whole bunch of stuff you know. An implicit method means essentially that you have more than one unknown. So rather than just having the one unknown at the current time step, you might have multiple unknowns at the current time step that you're solving for implicitly. So we'll walk through these methods and just ask yourself, is it single step or multi-step? And is it explicit or implicit? And again, we could have a single step, explicit or implicit method. Now, if you remember from boundary value problems, the main, and this is why we do them first, there's really only one primary property that we're concerned with, and that is accuracy. And that's given by the truncation error. So I just look at, is it a first order accurate or a second order accurate or higher order accurate method? And that tells us most of what we need to know about the accuracy of the boundary value problem, the solution technique. In initial value problems, we have the same accuracy concern, so we're still concerned with that property. Given by the truncation error, it's now first order or second order accurate in time rather than in space, but it's the same idea, same issues. But in addition to accuracy, we also have an additional property that we're going to be concerned with, which is a little bit more difficult, and that is numerical stability. So the question is, because there's always round-off errors in our solutions, which we've talked about before, the question is what happens to those round-off errors. They're always there. They're like disturbances. They act like disturbances within the solution. And the question is, do those disturbances grow with time, or do they decay with time? If they grow with time, then the algorithm is numerically unstable. If they decay with time, then it's numerically stable. So this is going to occupy a lot of our considerations in Chapter 9. Again, it is a little bit more difficult, and we'll have to walk through that very carefully. So what we're going to do is we're going to, as usual, start with the simplest methods for the simplest problems, and then work our way up to more complicated scenarios. So we'll start with first order initial value problems, and then extend to more general scenarios, and ultimately to PDEs. So first we'll do single first order initial value problems. So one equation that's only first order in time. And so in that case, u of t is just a scalar function. Then we'll consider systems of first order initial value problems, where now u of t will be a vector function. So there are multiple u's, u1, u2, u3, all of which are functions of time. So if you remember the Saltzman-Lorenz problem, we had a vector of three u's, u1, u2, u3. We actually called them x, y, and z, functions of time, but you can think of them as a vector of u's. And then we'll look at higher order initial value problems. So we're starting with single first order, then systems of first order, and then higher order initial value problems. And basically, once we know how to do systems, we can do higher order, because we'll show you a technique for converting higher order initial value problems into systems of first order initial value problems, which we can then use the techniques for systems to solve. So we'll walk through each of those as we go through. And so as you can see, we'll start with single step methods, then there are some additional methods. We'll talk briefly, just a brief overview about multi-step and predictor methods before we move on to PDEs. So in the next video, we'll look at first order explicit methods.